All right. Hello and welcome to the 5th webinar for student teams this year. Today's talk is on structural analysis and design for Formula SAE with MSC Nastran and MSC Apex. Today's speaker is Alex Satmarie. He's an academic consulting engineer with Hexagon. Alex was previously a professor of mechanical engineering, focusing on computing and design at King's College. With Hexagon, he helps students and professors put our software to work. He focuses on creating classroom curriculum with Hexagon engineering simulation software. And with that, I'm going to turn it over to you, Alex.
Great. Thanks, Alex Art. We're going to be talking about 3 big things, and then we'll have a part for wrap up. So the first section is just going to be an overview of structures simulation, thinking about how that connects to Formula SAE, what tools Hexagon can offer. And I also want to talk about how, in the long run, learning structural simulation, finite element analysis can benefit your career. What are some of the specializations you could go into that you might be able to start practicing right now in Formula or similar student competitions? And then I'm going to show 2 demos. The first one is going to be analysis of an upright. We're going to treat it as aluminum, just a simple metal. That'll be a basic finite element demo. And then the next demo after that is going to be an analysis of a composite panel, and we'll be doing nonlinear finite element. There's going to be a real increase in difficulty. And taken together, this webinar is going to go pretty long, more than an hour, maybe close to an hour and a half, because I'm going to be giving you a lot of details, and you should be able to follow along step by step on your own. And I'll wrap up by telling you about how to access Hexagon software, and also how to learn more and how to keep up with subsequent webinars. Let me tell you a little bit about Hexagon. A few years ago, Hexagon acquired a company called MSC Software, and MSC really, our claim to fame is that we had helped to develop and then we commercialized Nastran. Nastran is short for NASA Structural Analysis. NASA, of course, is the United States Space Agency. We have a very long history of excellence with finite element software, especially in the aerospace industry, but Nastran is used a lot in the automotive industry, and I'm going to describe more about that. And really, Nastran and our related finite element tools can also be used for any real purpose for finite element analysis, including things like the Giant Magellan Telescope, heavy equipment, shipbuilding. So in the student competition bundle, you can get the tools that are shown in this green rectangle shape. And some of them are not really tied to finite element, but they're worth mentioning, like Octron for acoustics and Atoms, Romax, and Cradle, which we've discussed in previous webinars this year. And then inside the blue rectangle, that's what we offer for finite element analysis. Unfortunately, CAE fatigue on fatigue modeling is not a part of the student competition bundle, but almost all of our other finite element tools really are. Nastran, of course, is our main finite element solver. Mark is another solver that is worth your attention. It is great at advanced nonlinear, like for forming processes, machining processes. It can handle really interesting materials. And another solver is Ditran, which is good for analysis, including crash analysis, which can be very difficult to handle because it's happening really fast. To be able to use these solvers, you also need pre and post processors. And I'll be focusing on MSC Apex, but Patron is a preprocessor that we've had for a long time, and it is the one that has the most complete support for Nastran. Mark has its own preprocessor that's bundled with it. And 2 more things to mention are Digimat for materials modeling and Apex Generative Design. And I'm going to talk about those in relation to one demo and then the other. So where can finite element take your career? One direction is global finite element modeling. And this is something that Apex particularly excels at. Where people normally are learning finite element in an introductory course. They're normally focused on stress analysis of single parts or a couple of parts. But for us to be able to model something like the boom crane that I'm showing in this video, you need to have a coarser model, and it takes a lot of craft to build a model like that that can tell you what are all of the loads that are going to be between different parts in the model. One of the keys for this model that we can see in the video is that there are a lot of not just solid elements, but mostly shell and beam elements, which are very economical. You also might notice connectors being assigned, multiple coordinate systems being used, and Apex is really great for setting up that kind of a model. Global modeling is used extensively in the aerospace industry, and one of the reasons why MSC Nastran is the gold standard in aerospace finite element modeling is that it has a feature called modules, which lets you break down an aerospace structure, or really any type of structure, into different components, and you can analyze those components in detail and hook those more detailed models together, letting you mix and match simulation results in an efficient way. So if you're at all interested in aerospace, but you're on a formula team, Nastran is still worth your attention. A lot of where our tools are used is actually in dynamics, linear dynamics, and we might be looking at what is the time evolution of the motion of the arm on a boom crane, or we might be looking at how does a vehicle or a structure respond to different types of excitations, like vibration analysis. In particular, in the automotive industry, an area that's very hot is called NVH, noise, vibration, and harshness, because a lot of what dictates whether somebody picks one car versus another car is how comfortable the ride is. And for that, you need to be able to do full vehicle simulations that are dynamic. And MSC Nastran, a lot of why it's used in the automotive industry is for NVH analysis. The next finite element technique that I want to describe is nonlinear. And by nonlinear, I don't mean you're dealing with something where it's not a straight line, but a mathematical nonlinearity. Let me just give you some practical examples of what that could mean. So we might have a forming process, like here's a mandrel in a tube, and to be able to shape the tube, to bend it, we would need it to yield. And that yielding is a nonlinearity. So that's what we call a material nonlinearity. We might have complex multiphysics, like here we have a bimetallic strip that undergoes a large deformation. So we would need to use nonlinear modeling for those reasons. And again, large deformation is one of the principal reasons why we need nonlinear analysis. So if we have this gasket sliding off to the side, and we have angles between elements changing, then we need nonlinear analysis. And finally, contact, like for a brake pad, that's something where we need nonlinear analysis. So if you're doing detailed parts level modeling, maybe for design of machines that involve contact or large deformation, or maybe for forming processes, that for us to be able to make anything, we need to be able to model not just how it works, but also how you make it. Nonlinear is relevant for all of those things, and learning it can really advance your career. And I hope you can see that many of these techniques are also relevant to Formula SAE. Still, a lot of the critical finite element applications for formula, let me see what comes to mind. One is, of course, looking at individual parts and making sure that they have good dimensions so that they're not going to fail, make sure that they're going to be strong enough under the loads that you predict. One of the structural analysis tasks that is particular to vehicle dynamics is making sure that the torsional rigidity of the vehicle is stiff to keep the tires on the road in the way that you desire. And finally, if you are wanting to make sure that the structure is safe, especially to demonstrate that a composite structure is equivalent to one that's made out of welded tubes, a space frame structure, then finite element analysis can be very helpful for design of things like composite sandwich panels, so that when you go to make your 3-point bend test specimen, you can get it to pass the first time. Okay, let me set up this first demo on analysis of an upright. So here's the geometry of the upright. The steps that I'll work through are, I will mesh it. I'm going to clean up the geometry just a little bit, apply a constraint to the bore, and I'm going to apply forces to it. one at the upper control arm, one at the lower control arm. And then we'll look at the material properties of this upright. We'll treat it as aluminum, enter these numbers, and then we'll set up the simulation and we will look at some sample results. And I will mention that there are some things that are a little bit distinct about this design. This is a rough preliminary design, and it is going to fail in some places. We would want to go back and add material to be able to make it stronger where we need it to be stronger. And a lot of how this model is set up is so that it can match with a case study for Apex generative design. I'll say more about that at the end of the demo. So let's go to Apex. So here is MSC Apex. And again, this is one of our main preprocessors with Hexagon software. I'm going to orient you to the user interface a little bit. These buttons up here let us control what we see. These let us control our model state, going from geometry, mesh, loads and boundary conditions, and then we can assign material and element properties down there. As we build the model, we will see things appear in the model browser. And when we go to set up the simulation, we will go to the study tab. Finally, we will go to post-processing, and that button will let us access that. Okay, let me first save my model. And I'm going to import the geometry. One of the first questions that I get from students who are considering using Apex is, can it work with my CAD model? And the answer is almost certainly yes. So if you look at the file types that we can import, we can do SolidWorks, NX, Inventor, Cassia, and ProE. We can also import any file that you can make as an STL or IGES or step files. So those are different types of interoperable file formats. And we're actually going to import this file as a Parasolid. Incidentally, Apex's geometry kernel is Parasolid, and so it works really nice with that format. I'm going to share these geometry files with you, really everything that you would need to do, these exercises, and the completed project files. I'll share all of that with you on SimCompanion after this talk. Okay, so here's the part, and I can rotate my view by clicking and dragging with the middle mouse button, and I can pan my view by clicking and dragging with the right mouse button. We're going to mesh the part. I'll go to the meshing panel and pick solid mesh, and we're going to use a 2mm mesh. Tetrahedral elements are the easiest to mesh with. They easily conform to a geometry. We're going to use quadratic elements. You don't want to do linear tets if you can avoid it. So I simply clicked on the part and it's meshing right now. Let's check out the quality of this mesh. Remember that we can change how we visualize our model using buttons up on this bar. And we're going to look at element quality. By default, Apex will calculate quality for 2D elements, but let's look at 3D. And we see that we have 80,000 good elements, 57 poor elements. That's not a problem. And 88 bad elements. So this is overall a pretty high quality mesh. We can expect it to give us good results. Still, let's see if we can take care of some of these bad elements. I'll right click on the bad button and click show only. So we're going to see only the bad elements. And we see that a couple are in random places, but some seem to be falling together. Maybe we can do something about that. I'm going to right click on bad again and click show associated geometry bodies. This gives us a wireframe view and is going to make it easier for us to relate the bad elements to the overall geometry. So let's take a look. Do you see how there's these elements that are really squashed? What's going on? Well, I have an edge in my part file here and another edge right near it. By default, Apex doesn't let elements span edges. Edges are boundaries for elements, and this helps us control the mesh. But if we don't really desire this edge here, and if it isn't meaningful to the geometry, we can disable it. So I'm going to go into Geometry Edit. We have a huge menu of tools that we can use for editing our geometry. And these are really meant not for creating a new geometry, but for tweaking a geometry to make a part more easily meshable. So we could like push pull on faces, we can do revolve and sweep. These are similar to operations that you would see in a solid modeling CAD tool. All that we're going to use today is the suppress feature. So I can click there, and now I'll click on this edge. And Apex is turning that edge off so that elements can span it. And now you see that the elements are much more relaxed in this area. Let's take another look at element quality. We see that the number of bad elements has gone down to 74. So that's nice. We knocked down more than 10 bad elements. And we can just look at the mesh here. We see that it's much smoother. We still have this edge here, and I'm going to click and remove it. That'll take a little bit of time. Now, normally, a geometry edit operation like that will happen much faster if you haven't already meshed the part, but I meshed the part so that we could see the effect of these operations on the mesh. And look at that. Now we've got an even smoother geometry, and we've gone from 74 now down to 65 bad elements. Let's see if we have other opportunities for improving this mesh. Let's see, these bad elements are kind of unavoidable because of how these two edges are just tapering together. It might be good to add a fillet into that geometry, but that's really the CAD operator's job. But overall, this is a reasonable mesh. It is a little bit coarse, too coarse to give great stress analysis results. We're only seeing 1 or 2 elements across the thickness here. I would call that 1 element across the thickness. I'll show you results with a more detailed mesh later, but this is going to be good enough just to show you what the workflow is. Now let's apply loads and constraints. We'll do constraints first because that's a little easier. So I'm opening up this constraint tool, and I'll take this as an opportunity to explain the general structure of a tool in Apex. One of the first things you might want to adjust is the tool execution mode. If it's highlighted, it's an automatic. That means that Apex is going to be very eager to take action, even if that's not what we intend. Or I can turn that off, and I'm going to need to explicitly confirm more of my actions. That's okay. That's going to make it easier for you to see exactly what I'm doing. This part here is the pick filter, and I'm just going to focus on picking different entity types so we can make it so that we only pick solids. Right now I'm picking nodes by default, and we're going to want to use faces to be able to pick this entire face on the inside of the bore. And we'll get that fully constrained, and this default constraint type is going to work fine, but there are other types of constraints that let us control which degrees of freedom we're constraining. So I'll click on the bore, and you see that that face has been selected, and I will middle click to confirm. And now the constraint is applied. And I see that constraint over here in the model browser. Oh, and actually we can look up here. This is the part file that I had imported, and here is the mesh. Great. And if I close this tool, I can even, this is kind of a funny part file name. I could click on this and change the part from break to upright. Okay. Now let's apply forces. First, I'll apply a force to the upper control arm. Now, we're going to want to apply the force using something called discrete ties. That if I simply click on, well, one node there, that's not really going to give us great results because we will get a singular stress being applied. And if I click on the entire bore, what will actually happen is that same force gets applied to every node in that hole. That's also not what we want. If you want to know more about applying loads to solid elements, I have a whole YouTube video on it, and I'll share a link with you later on how to do that. A simple way to get loads applied across a surface in a reasonable way is to use discrete ties, or we could call that remote force application in this tool. And Nastran calls these RBE2 and RBE3. You can use rigid discrete ties, but those add stiffness to the model, so I will use compliant. And let me set up the numbers for the force that I'll apply. We'll use a scale factor of 1 unless we have a reason to do otherwise, and I'll enter the vector components that I'd indicated on that slide. -8, -97 in the Y, and -236 in the Z direction. I'll click faces in the pick filter so that I'm picking not nodes, but again, those faces, and I'll click on that hole. And then I can use my scroll wheel to zoom out. I'll click on this hole also. Oh, I was in automatic tool execution mode. I could just undo. And let me turn that off. And that's going to make it easier for me to select those two different holes. So I'll click there. and there. And now in this selection stages interface, I can see that I have two faces selected, and I can middle click to proceed through this process. And now it wants me to pick a place to actually apply that force, right? A force has to be applied at a coordinate. And I want to get somewhere in between those two. And I picked average points in the pick filter. That will let me pick a point that's the average of all of the nodes on those two faces. A nice way to get that force centered. And finally, I can middle click to confirm. And I can rotate my view and see that the force is applied right there. So here's the force vector, and these purple lines represent the discrete tie that's tying that force to the nodes where it's ultimately getting applied. Let's do this process again for the lower control arm. So let me zoom in there. And I'll enter my force components, 493 minus 9. And again, I'll pick those two holes, middle click, and Apex remembered that I'm going to want to be picking based on bases and average points. I'll rotate around. Yes, I have picked that average point. That's great. And I'll middle click to confirm. Next, we'll create material properties. This is one of the points on which I see people who are new to Apex struggle the most. It's a three-step process. Step one is to actually enter the material properties. We're going to tell Apex what aluminum is like. Now, there are a lot of choices you could make with this form, and I'll go into more detail on that when we do the honeycomb sandwich panel example. But for a metal, by default, the settings are pretty simple. We just need to enter the material properties. And I'm using units, I should say, of megapascals, millimeters, kilograms, and newtons. So our stress unit, again, is megapascal. I want an E of 70 gigapascal, so I can type 70E3, and that will convert it to gigapascals, instead of me having to type in all those zeros. I don't need to give it G. Apex can calculate that, or Nastran can, rather. I'll enter the nu of 0.33 and a density of 2.7 times 10 to the minus 6. Now, we don't really need the density for the static stress simulation, but it's also often handy to do a normal modes simulation for troubleshooting, so I normally enter a density anyway. The second step of applying materials is to create element properties, which let us join the idea of the material properties with how they're represented on the elements in the model. So I'll create a 3D element property and call it aluminum 3D. And I'll pick a material ID of aluminum. So I've created that element property. It was one more step, but it was an easy step. The third step in the process of assigning the properties is to actually assign this element property to the part. I'll click this button and I'll click on the part. And we were in automatic tool execution mode. And so now the part is aluminum. So now we're ready to go set up the simulation. There are a couple of ways that you can have scenarios work, and a lot of the tutorials that I already have on YouTube show something called legacy scenarios. But here we're going to use new scenarios, which give us more access to different features in Nastran. And clicking on the Study tab, I'll right-click on Study and click Create Scenario. There are lots of different types of solutions we can do. So we can do normal modes or different types of dynamic and frequency responses, and we can do nonlinear. We'll do that in the next demo. But for now, we'll just do linear statics. I'll click OK. I'm going to associate the model representation. This says which parts we're going to look at. There's only one. I'm going to pick, I can pick the entire model assembly, and that will definitely pick the part. I'll click OK. Now let's go to Loads, Constraints, and Initial Conditions. I'll double click on that. So we need to actually assign the constraint to the part. I can open up Constraints, and I can pick the one constraint, so that was easy. Next, let's go to Loads. I have two different forces that I'm applying, and I can click on this radio button, but if I click on that one, it unselects the first one. And the way to get around that is to make a load combination, which is like a new force that's a combination of other forces. And I can create that right here. If I had really wanted to do that earlier, load combinations are also available in the load and boundary condition tools. So I'll click Create New Load Combination, and I'll select those two loads, and I also need to enter a scale factor, and again, I'll just use 1. And Apex has picked that new load combination for me, and we have a checkbox saying that we are going to apply those loads. Let's double check and see that we've got constraints being applied and the right one is picked, and I will click OK. And now we are ready to run the simulation. If we wanted to consider more load cases, if we had more loads in the simulation, we could create more load cases by right-clicking there and clicking Add Subcase. To actually run the simulation, I can right-click on the scenario and click Run Simulation. It also can help to rename the scenario. So you click and then click again to get it to be renameable. And I'm going to enter like upright, linear, and that way my results files that get stored on my disk are going to have a reasonable name for later reference. Instead of running this simulation, I'll show you some results that I already have put together so that we don't have to wait to watch the solver run. And actually, in this example, I have put together more load cases that combine different types of loads for things like steering events or cornering. Let's go to post-processing. Okay, in our post-processing interface, this panel lets us pick which scenario we're looking at. You could have multiple different scenarios in your Apex project, and you can switch between them here. We can also pick between different load cases. So right now we see stress results for static. Let me zoom out a little bit, but here I can double click. And now I'm looking at the braking subcase. I had already opened this up and changed my view, and that's why the part had scooted over there. I can change my view settings, and we'll need to do that some with the honeycomb sandwich panel example. And we can change which quantities we're looking at by clicking down here. Like I could make a vector plot of displacement results very easily just by clicking this vector. So we see a lot of vectors, one for each node, showing how each node is displaced. Coming to the bottom, we can get some more control over how our model looks. So for the deformed shape, we can change the scaling. That what we see here is very exaggerated because otherwise we would have trouble visualizing the extent of the deformation. But I can click true scaling, and that shows us exactly how much the part would have deformed under this load in real life. We can turn the fringe plot on and off by clicking this button, and I'm actually going to turn off that quiver plot. You can get some control over the fringe plot by grabbing this panel here. See, this normally just looks like a color bar on top of my plot, but if I mouse over, I can grab this window and I can click this expander, and that will keep it open, and I can modify things. So this is saying that we have a peak stress of 3.7 gigapascals. That's really bad. I will enter 100 megapascals, which is still a lot for aluminum, but as an exercise, this will show us areas where we really need to strengthen our design. So for a lot of this part, the stress is pretty low, it's not concerning, but where it's red, we probably need to make things a lot thicker. So up here on this surface and down here and here, those parts, but like the corners, the locations of our holes, the sizes of the holes, those seem to be pretty appropriate. I can change what stress quantity I'm looking at. I can change what quantity I'm looking at by clicking here. So I could pick things like displacements. And if I had set things up a little differently, I could have looked at strain results. You'll see an example of that later. I can change what type of stress I'm looking at. I normally use von Mises for looking at failure of metals, but maximum shear stress has value for interpreting things. We can look at the X component of the force. We can look at principal stresses, Tresca. It all depends on what you're interested in, what failure theories you're using, that kind of thing. We can turn off nodal averaging, and that helps us look at the quality of our results. So by default, averaging is on, which makes it easier to interpret the stress results, to read them. But if we turn off nodal averaging, That's good for just trying to figure out, do these results really make sense? So when we zoom in here, we should see that the stress is going in one direction. If you see stress rising kind of backward across an element, that means that you need to refine your mesh. And this mesh is okay, I think, for giving us results across the thickness of this part, but probably not great for giving us converged results along these fillets. It might give us a ballpark understanding. Okay, so I'm going to turn nodal averaging back on. We can read exact stress results using the probe tool up here. I will click on that and click fringe. So this will show me the fringe results. And as I mouse over, numbers appear. I'm going to click and leave a marker. This white number here is the node number. Every node has its own ID number. And the yellow number is the stress, in this case, 1.28 gigapascals. So that's a lot. Okay, so this concludes the demo on the upright. Let's go back to the slides, because, you know, if I wanted to, I could go back to CAD and I could change the geometry, but I wonder if there's a better way. I could just iteratively change my geometries in CAD, bring them back into Apex, repeat the analysis manually. Or another approach is I could use a generative design tool. There is Apex generative design, where instead of saying, here's my part geometry, here is my loading, where is it going to fail? We could instead ask the question, here's the overall envelope where we want the part to fit. Here are the interfaces, the loads, and my failure criterion. Solver, you go figure out which shape the part could have. So this is an advanced optimization technique. It doesn't just let us size individual dimensions on the part. It can create these organic geometries. And this is a case study from, I think, the University of Paderborn's Formula team. And they used generative design to be able to lightweight their uprights. We have a related tool called Nastran Sol 200 Neo, and that uses a lot of the same solving power. And there will be a webinar focusing on that for Formula in 2 weeks. Now let's move into the composite panel section. To be able to use composites in Formula on, you know, anything that's critical, load-bearing parts of the structure, we need to be able to show that the composite results for test sections are good. And for us to be able to work out, is a test panel likely to work under mechanical testing, we can do simulation first, and I'll show you a workflow for that. And I'm not going to do it with the exact dimensions and parameters that you might use for real in Formula, but the overall workflow should be relevant for you. We're going to use a little tool that I've made to create the geometry, right, in Apex. And for you to be able to use that tool, you'll need to get oriented on what the different dimensions are. So the thickness of the sandwich panel, I call height to distinguish it from the thickness of the walls of the honeycomb. We also have radius for the hex cells, which is also the same as the edge length of the hexes. We're going to put this in 3-point bending, and we can use span to describe the distance between the two supports. And the panel, of course, has its own overall length and width. And so you would want to enter those into the tool that I'm giving you. Here's the overall workflow that we're going to use. We're going to, again, generate the geometry using a Python macro in Apex. And we will generate the mesh. We're going to use quad elements. So those are shell elements, not solid elements. And we're going to connect them across different faces of the model using mesh-dependent ties. We're going to, for our loads and boundary conditions, use regular SPC constraints. And we're going to apply the load not with force, but as an enforced displacement, or what we call an SPCD in Nastran. And that's going to help us test it approaching failure and in a really numerically stable way. We're going to apply many different types of material properties. Here's the Nastran terminology. Matte is what we normally use for isotropic materials, and that's what we used for aluminum. But we're also going to look at the yielding of the aluminum with a matte AP for elastoplastic. We'll use matte 8 for isotropic material properties for the composites, and matte F to look at composite failure. We're going to create composite sheets and then stacks out of those sheets. We will assign element properties similar to how we did it for the upright, but it's going to be a little bit more complex. And then we're going to have to do some work to make sure that our elements are actually set up and oriented the right way. We're going to do offsetting, which I'll demonstrate graphically. And again, we need to be able to tell Apex which direction our composites are oriented. As examples, I will create linear and normal modes scenarios, which are good for troubleshooting, and then I'll give you more detail on how to do a nonlinear scenario and how to manage a nonlinear run. And then I'll show you post-processing of composites, which takes just a couple more steps than you would for linear materials because it's a little bit more complex. So I'm going to pull up an Apex session and we'll get to work. Okay, so we're back in Apex. I'm going to save my project, and I'll save it as CSP, and I'll use today's date. Next, I'll create the geometry. I'll do that by opening up the macro. So I clicked macro, and I'll click play macro. And we're going to use a script that I'll give you later on Sim Companion, and I'm just finding it on my computer. Okay, I'll double click on honeycomb, and Apex will give me a little dialog box. And for me, that appeared on another monitor, and for you, it might appear behind the Apex window, so you may need to poke around to find it. But we can enter the dimensions that we want in this form. And here are the dimensions that we're going to use. We will use a cell radius of 6.4 millimeters, a height of 10, a length of 250, width of 96, and a span of 220 millimeters. Now, these aren't the exact dimensions that you might want to use for a real honeycomb that you're really doing in the standard way that is prescribed by SAE, but this is going to give us dimensions that make it easy for you to see what's happening in the workflow, and I'll let you work out on your own how to make the model work with different dimensions. Okay, I'll click OK. And Apex is now generating the geometry. It is doing sketching operations that a user could do using the geometry create tool, but it's doing it a lot faster and more precisely than I could to be able to create all those edges. First, Apex is creating edges in the W direction on the honeycomb, and now the script that I've made is making it add edges in the L direction. So for honeycomb, it's made by taking multiple layers and adhering them together in certain ways such that when you expand it, that honeycomb shape is formed. And because some layers are adhered together, they have double the thickness of other layers or other faces. So those faces that are in the L direction, like this one, are going to be twice as thick as the ones in the W direction. The W direction going like this, and that's a big part of why honeycomb is a lot stiffer going in one direction than another. And I'll mention my units. I'll show you how to change units. We can go to Options, Application Settings, and click Units and Parameters, and right here, millimeter, kilograms, seconds, newtons, Kelvin, and I actually have it set so that it's going to use degrees instead of radians. I'll click Cancel there. Next, let's mesh the part. I will click on Mesh. Surface mesh, we'd done solid earlier, right? But now we're dealing with surfaces and shell elements. I'll use 4 millimeter elements, and I will click here to do quads. And linear quads are often quite fine. And I'll select the whole part, or the whole assembly, right? Which is made of multiple parts. And the way that I made the geometry, I actually have it so that all of the faces for the zigzags in the W direction or the horizontal parts in the L direction, they're not all physically continuous, but Apex is treating them logically like individual separate parts. So all of those horizontals are one part together, and that's going to make it a lot easier for us to assign material properties. Okay, so we have all of these things meshed, but the meshes aren't congruent. To get the meshes connected, I'm going to go to Interactions and click Mesh Dependent Ties. And I'm going to, in this case, just connect everything to everything. So I selected everything, middle click to confirm, and select everything, and middle click to confirm. And that will take a little bit of time because Apex is going to look at all of those parts and figure out which ones touch other parts. That's not brutal for this example, but if I were wanting to deal with something like that boom crane that I showed earlier, I might want to be more particular about exactly which faces I am connecting to which edges with a mesh-dependent tie. Now, my whole part looks like it's kind of blue, and if I zoom out, it's like not really visible. And the reason for that is as we zoom in, we can now more distinctly see these icons or symbols that represent mesh-dependent ties. So that's showing how all of these different meshes on each of the different faces are linked together now. For me to see what I'm doing, I'm going to turn off those interaction markers by clicking that button. And now we'll close the mesh-dependent tie window. I'm going to apply loads and boundary conditions. Let's start with constraints. Now, because we're dealing with shells, clamped constraints are not really what we want. We want to use a general constraint so we can pick the exact degrees of freedom that we want to control. So we're doing X, Y, and Z along this edge right here. And this tool was in automatic tool execution mode, so it applied that constraint right away. I'm going to disable the X degree of freedom, and that's going to let these nodes here kind of slide. So this is like a simply supported beam instead of having both of the supports be pin connected. And I think that's going to give us more realistic results, allowing for some slip on the test rig. I've created that constraint there. Next, we'll apply an enforced displacement where we would have, the indenter pushing down on this part along this edge right here. I will click enforced motion. I'm going to enter -30, so -30 millimeters pushing down, and that should lead to pretty extensive deformation. We'll see how this structure does under this kind of loading. So I'm going 30 millimeters down, and I'll click on this edge here, and the enforced motion is applied, but for it to be active, I will also need to do what this dialog box says. So I need to apply constraints that control the same degrees of freedom as the enforced motion. And that will tell Nastran to treat those nodes in a special way. It seems a little counterintuitive. I really want those nodes to move, and so it looks like I need to constrain them in a way to keep them from moving at all. But this is how it works. So I'll click translation in Y, because that's the direction that I want to control. I'm zooming in to make it easier for me to pick that edge. And so I've added in a constraint there, and that's going to let Nastran handle that enforced displacement in the way that I intend. And to assign materials, I'm going to use another macro just to save a lot of typing. So I'll click macro and plain macro, and we'll use create materials honeycomb. Now, if you're using different materials, this would not be very useful for you, but you would want to use this if you're just following step by step through this tutorial. So Apex has made all of my material properties, but I'm going to go talk you through all of the techniques that you would need to do to achieve that. So for the aluminum, we have isotropic parameters similar to what we had before, but we also have elastoplastic properties. And to create those, I had clicked Add Material Model, or rather the script did the equivalent of that. And then you can check elastoplastic. And now we click on elastoplastic here on this list, and we're going to be entering the data for this elastoplastic response as a table. And I will click Add Table, and we can load the stress strain curve from a CSV file. So I'll open aluminum plasticity, and this button here is what we use to load that CSV file. Here is the stress strain data, and note that we're starting at a strain of 0, and we have a stress of 250. Well, that doesn't make sense. It doesn't make sense for a total stress, but this data we have measured relative to the onset of yielding, so relative to plastic strain, right, not total strain. So I need to change this dropdown to be able to get the model to run it all. And I will click OK. So that does it for the aluminum properties. For the prepreg, you would need to change from the material model being an isotropic mat 1 to a shell orthotropic mat 8. And we would enter the parameters here. Now, for this particular prepreg, the stiffnesses in the X and Y direction are effectively equal. And so that's going to mean that I can use a pretty simple layup. But if you have different strengths in X and Y, which is very common for composites, you would need to use a different layup than the one that I'll be showing you. And of course, with this being a composite, the in-plane shear is much lower than the X and Y stiffnesses, about 65 gigapascals versus 3.3. We can model composite failure by adding in a failure model using this add material button, just like I did to pull up the elastoplastic properties. We're going to do, there's different ways that you can model how the stiffness degrades, and which one you use is really an engineering judgment. There are good reasons to do immediate. I found that gradual stiffness degradation at least made it easier for me to obtain results. This is something where it's your responsibility to figure out what's right for you and your design. I've enabled first failure criterion, and I'm using Hoffman failure, but you could use SciWoo or Puck or what have you. We would also need to enter an allowable shear stress for interlaminar ply failures, and we would want to check progressive failure. So that's the material properties. Now we need to go from materials to making sheets out of those materials. For this example, I'm going to just do one sheet. I'll click Create Sheet, and I got into Sheets by clicking on Sheets Stacks there, by the way. And you can change the name of the sheet. You can pick the material. I'll do the prepreg, of course, and I'm going to give it a thickness of 0.25. Now, if your design involves multiple different composites, maybe a weave and a unidirectional tape, or different weaves of different thicknesses, you would want to create multiple different sheets. And next we can define our stacks. I'll click Stack, click Create Stack, and I'm going to click Sheet to bring in that sheet that I just created. And if I had multiple sheets, I could just click that button over and over and pick each of the different types of sheets. I can select multiple layers and right-click and click Duplicate Above. I can enter angles right in here. And I'm going to enter one more sheet above. If I wanted to be able to change the direction of some plies, I could select them, right-click, and click reverse order. So there's a lot of control here in how you have your stack set up. And we see that we have a total thickness of 1.25 millimeters. And we could rename the stack if we wanted to. I'll just leave it as stack 1. Next, we'll create and assign 2D element properties. Remember that the thicknesses of the aluminum in the honeycomb going in the W and L directions are going to be different. So I'll make one property called aluminum T for thickness, one level of thickness. I'll pick aluminum, and let's do a wall thickness of 0.01 millimeters. And I'll make another element property, and I'll call it aluminum 2T, and it'll have double that thickness. I'll pick aluminum again and do 0.02. And now I will assign my 2D element properties. I have aluminum 2T picked here, and so I'll pick on the L direction faces. And I can pick aluminum T here and pick these zigzag W direction faces. Next, I'll create another element property for the composites. And if you had different layups in the top and bottom, it would be a good idea to have separate properties, separate element properties for those two different stacks. And I'm going to, instead of doing P shell, do composites and click P comp. And I can click stack to import that stack that I'd created. And actually, I could do the entire composites workflow of creating sheets right in this interface by clicking local, but it's a little bit small. Okay, I'm about to show one of the easiest mistakes that you can make, so pay attention. For us to be able to view the composite results, I need to take this pane, drag it to the right, and I can see stress strain output. That is no by default, but we want to change that to yes. And now I can assign these properties to the top and bottom stacks. So I clicked Assign Properties, the bottom stack, and now I'll click the top stack also. And we can confirm our material assignments by opening up this tab here, and I can mouse over aluminum 2T. I see that going in the L direction. Aluminum T goes in the W, and composite stack goes on the top and bottom. Wonderful. Let me show you some work for manipulating the element directions and positioning. So we can preview how Apex would think about, or we can preview how Nastran would think about these elements, these shell elements and their thicknesses with this shell thickness button, which by default just color codes based on thickness, but we can actually visualize the thickness here. So we only have surfaces and shell elements in this model, which are kind of infinitesimally thin, right? They're flat, but now we see them rendered with thickness corresponding to the properties that we assigned. And look, we've got a little problem here. Here is the honeycomb, and it goes up halfway through the composite stack, and similar at the bottom. The reason for that is that by default, shell elements are treated as being at the midpoint of the material, but we want the shells at the top to actually represent the bottom surface of the composite stack, and the ones at the bottom to have their top surface match the bottom of the honeycomb. So we can fix that by using offsetting. I'm going to go into attribution tools here and click thickness and offset field, and we can change the offset here. I'm going to enter the offset as the half of the thickness of the stacks, so 0.625 millimeters. And I can click on this top stack to bring it up, and I'm going to change this offset now to a negative number to bring it down on the bottom. I'll click there. And let's turn our 3D viewer back on. And now we see that we have the honeycomb not touching the midplane of my composite stacks, but touching the bottom of the top stack and the top of the bottom stack. Fantastic. Now for this exact exercise, the composite's x direction is aligned with the global x direction for my finite element coordinate system. But if I wanted to change that, I could use something called a material orientation field. I could create a coordinate system for my composites here using this coordinate system tool, and then I could assign it again using the material orientation field. I'll let you figure out the exact details of that on your own. Whenever we're working with shell elements, it's also good to be careful about which way are they pointing, right? Which is the upside and the downside of the surface. We can use this tool here to show those normals based on color, or we can use vectors, which I think is going to show a little more easily for us. And we see that for the top stack, we have the vectors all pointing up in the y direction, and the bottom stack, they also point up in the y direction. But maybe you had two asymmetric plies and you want them pointing in opposite directions. You could select the elements down here and flip them using, you would go to not the regular meshing tools, but these fem edit tools. And then you could click on element orientation. That technique is a little bit advanced, so I'm not going to work you through it today, but you can figure that out on your own. Now we'll create scenarios. A lot of the time when you're doing a nonlinear run, you should first do a linear run anyway, just for troubleshooting purposes. It's going to go pretty fast, and you can make sure that your loads and boundary conditions make sense. All of the reactions add up. I'll set that up just like we did before. We associate the model rep by right-clicking on the model representation. And, you know, if I wanted to just model the top stack as a checkout run, I could do that too. So that's why it's useful to pick the model rep. Here, we'll pick the whole panel and click OK. I'll double-click on loads, constraints, and initial conditions. I'll click constraints and create a new constraint combination to pick my two simple support constraints, as well as this kind of virtual constraint that we're creating for applying the enforced motion. I'll click the apply checkmark, and I'll close this panel. And we see that that's selected. That's great. And we only have one load, the enforced motion. I'll click OK. And then we would be ready to right-click on that scenario and run it just like before. I need to show you something about a normal modes simulation, which can be great for troubleshooting a model that is under constraint. So I'll right-click on Study, click Create Scenario, and we can do normal modes with Sol 103. This is principally used for doing vibration analysis, but again, is useful for troubleshooting constraints. And as before, I'm associating my model rep, and we could add loads, constraints, and initial conditions. I normally just pick the constraints and not loads for a normal modes scenario. Forces are not entered into the normal modes. I'll click OK. Now, for this to actually run, I'll need to tell it how many normal modes to extract. So we go to Simulation Settings, go to Method for Eigenvalue Extraction Parameters, and click this button here to create, edit, and delete something called an EigRL. I'll click Create New EigRL, and we want, say, 10 roots is good, or maybe 20. I'll enter 10. Click OK. And let me resize this panel. I see that I have a check mark and that this new EigRL is selected there. So now I would be ready to run the normal modes simulation. And I'll click OK. Finally, we'll set up the nonlinear scenario. And I'll show you some settings that can converge with the exact geometry that I've shown you, but you might need to use different settings for your situation. Nonlinear finite element can be very challenging, and it takes a lot of technique and craft to get a converged result and to get a converged result that's correct. This time for type of scenario, I'm picking Sol 400, and I click OK. And I can right-click on my model representation and click Associate Model Rep, and there's my model rep. I'll click OK. And like before, we will assign loads, constraints, and initial conditions. Now we're going to go to output. We're going to need to look at something called an FO6 file. And by default, Nastran will export your entire input file into that output file, which I find confusing and it makes it harder to read. So I'm going to change that to none. That default is there for a reason. Some people really do like having that information all in one place. So I'll change echo sort to none, and I click OK. Now we need to request outputs. So it's good to check constraint forces, make sure that it's checked and that plot is checked. If plot isn't checked, we won't see results. They'll be output to a different file. By default, when we're doing nonlinear, you'll see nonlinear stress plotted, but it also helps to select element strain and plot and element stress and plot. And I'll click OK. We need to set up our nonlinear simulation settings, and I'm going to pick NL step, create, edit, delete, create new NL step. There are a lot of settings that are available to me, and so I'm going to click General, Adapt, and Mech to open the ones that are going to be the most relevant for you. So I click General, Adapt. Now I need to scroll down to Mech. You see all these options here. Some of the most important ones are to be able to set your convergence criteria. P and V are good for starting with, but you might find that other combinations give you better convergence or faster convergence. You might want to do more iterations per time step, like change that 10 to 20. And the maximum load fraction, you might want to set that down from 0.5 to 0.05 to have Nastran more gradually apply loads to your nonlinear situation. Still, this is good for a start, and I think that's a reasonable crash course for nonlinear, but learning how to use all of the controls in here is worth your time in the long run. I'll click OK. And let's go to common settings now. And I'm going to go down to Material Options and click Parabolic Transverse Shear Stress Distribution. This will let us extract interlaminar ply stresses. I'll click OK. And now we can right-click on the scenario and run it, But we can also click export to be able to make something called a BDF file. This is exactly what Nastran would read, and then Nastran for us will produce something called an H5 results file. That's something that we would want to be able to bring into Apex. We could do all of that manually if we need to, and we do need to if you have a nonlinear run that doesn't converge but does produce an H5 file with results. You can attach those results by clicking Attach Nastran Results. I'm going to take a few minutes to show you what a BDF file looks like and a couple of other files that are essential for managing nonlinear jobs. So here is the BDF file, one similar to the one that I just created. This has all of the data that we're giving to Nastran for the simulation. And if I scroll down randomly, you'll see that it's mostly C-quad element information. So which nodes are we connecting? And grids, which define the locations of every single node. This is a big file. Oh, and I'm viewing this file in a program called VS Code. It is a free source code editor from Microsoft, and it has some nice modes that you can install, like VS Code Nastran, that let you get the details on BDF files. Here's where constraints are assigned, and you can scroll up and be able to see things like the exact nonlinear stepping parameters that we set. Remember general, adapt, mech, PV, convergence criteria. It's all in there. Here are some of the nonlinear options, like T-shear corresponds to that parabolic shear stress distribution option. Being able to think about an Apex model in terms of the Nastran input file that you create is essential for being able to look things up in the Nastran documentation. Now, let's say that we started our job, maybe through Apex or maybe by separately running Nastran and targeting the job file. A lot of files would be created, and as the job is running, you would want to review the .sts file, which gives you the status of the job. If you open it up in VS Code, it will automatically reload the file as it gets updated. We get one line per step of the nonlinear solution. And typically when we're doing nonlinear, the full load doesn't get applied immediately, it gets applied in increments, and more load gets gradually ramped up. That's more likely to give us a converged result. For a static scenario, we still have something called time, but it simply goes from 0 to 1 with, like if we're at a time of 2.59 e minus 1, so that's 0.26, we would have 0.26 of the final load being applied at that point. Looking through here helps us see how far are we through the job really, and the rate of convergence is going to be changing. So we normally start with pretty small time steps, but they might get bigger as the job stabilizes, or they could get smaller when you approach a convergence problem. So knowing how to read one of these files can be very helpful for troubleshooting convergence in a nonlinear job. Another result file that we get is the FO6 file that I mentioned. And again, by default, we would have the entire BDF file echoed into here. But as you scroll through here, you can see that there are details that might be helpful for troubleshooting. Like this gives us some information on the type of elements that we're using. If a job fails, it's very helpful to open up the FO6 file, hit Control F, and then look for the word fatal. But in this case, this job had converged. So let me show you an example with results so that we can see how to interpret composite results. So we're already in post-processing. The nonlinear results look a little bit different from what you would see with linear results. One thing is we can look at the different load steps by clicking on these orange lines, or we can step through them with this step forward button with 2 arrows, going forward or backward, or we can hit play, and this lets us view the deformation of the part. In this case, I have all of my steps available to me, but if you ever see this red triangle, maybe over there, you can just click and drag it all the way to the right, and that will let you look at all of the load step results. And I'm actually going to pick this point because where we get at the end of the simulation is the most relevant. Or you can click this button here to go to the last frame. Like before, we might want to look at stress results or NL stress, which is similar. But here we see that we only really have numerical results being shown for the aluminum honeycomb and not for the composite plies. And the reason is that that data is stored in a very different way, because for composites, we need data for each ply. I can come in here and I can turn off top stack to be able to visualize the aluminum. And in this example, the aluminum has yielded almost everywhere except for like at this point here. So that's something that you might want to make sure isn't the case in your model. Next, we can look at the composite results. So I'll turn the top stack back on, and we can open up composite ply stress. I'm going to open up this panel here, again, by mousing over and clicking on the expander. By default, we look at von Mises stress, which is not the most relevant for composites. Something like X component or maximum principal is typically more relevant for composites. We're seeing the data being read out for each different composite layer. And we see that the ones in the 45 direction aren't carrying too much load. That middle layer is doing okay. We can see for the top layer. Now you have to be careful in interpreting this because the color bar isn't fixed. And so you might actually have different peak stresses for each layer. Another type of post-processing result that we'll want for composites, especially if we're looking at failure, is the Nastran failure model, which I can access by clicking this button. And on this scale, 1 means that it is failed, and something like a 0.5 means the equivalent to some of the fibers have snapped. As a composite fails, it locally can significantly lose stiffness, causing it to actually relax a little bit, but then putting more load on related areas. And so failure can propagate in complex ways across composites. So here we see kind of a line of composite failure along the bottom. We have this metric going up to, that's 0.976. So that is almost failed. So with this exact model, I've got it dialed in so that it's approaching a complete failure of the composite. One final result that you might be interested in is the force displacement curve, which you can't do completely in Apex, but you can do it without too much trouble if you also know Excel. So I can create this vector plot here by clicking here, right? And that will show me the constraint reaction forces. And remember that for an enforced motion, that's similar to a constraint. And so that's how those results are tabulated. Okay, so I'm going to click the Z here so that I'm looking at this and I'm going to zoom in right near this set of nodes that are all along that loading line to make them easy to select. And now I will click on XY chart, and I'm going to use plot targeting to be able to say, I want to look at the loads on those nodes, and I will click and drag and middle click to confirm. And now I can pull out the constraint reaction forces, and those get plotted on this chart. So this shows me what the force is for each load factor, right? Each like amount of load that we've applied on each of those nodes. And we generally see it ramping up significantly. We can then export these results with this button, and that puts the data in a CSV file. So we can look at the loads for all of those nodes, add them up, and we get the total load. We can also extract the displacements by clicking here. And we could extract those plot results also into a CSV file, bring that into Excel, multiply force times displacement, and that gives you the energy. Or really, rather, you want to integrate the force over displacement to get the energy that the part is absorbing. So that would conclude this demo. Now we saw that the performance of this honeycomb sandwich panel is not great. The aluminum completely yielded, the composites were failing. How could we get a better composite stack? Well, let's go back to the slides. One way that we could do better and in a more streamlined way is with a tool called Digimat. Digimat is good for material modeling, and one of the approaches that it uses is based on finite element analysis. And so with that, we can give it things like detailed material information. Here's where all of the fibers are in this section of the composite. And Digimat can then calculate the material properties based on that. It's also great for other processes like additive manufacturing. And so it can predict properties based on how your process is configured. Digimat can work together with Apex and Nastran. One of the simplest ways that you can do it is to simply calculate your composite properties in Digimat and then enter them into Apex just by typing the numbers in, similar to what I did. And then Apex would run Nastran. But another approach is to work in Apex, export a BDF like I showed you, and bring that into Digimat. Digimat could then modify it, bring in its material properties, and have that work on Nastran. Finally, we could have Apex export a run-ready BDF model file, get that into Nastran, and then Nastran would be able to do a co-simulation with Digimat. You'll be able to find out more about this next week in the webinar from Gaurav Ghosh, focusing on composites with Digimat. The point is that by connecting Digimat to Nastran, you would be able to have Digimat do a lot of the optimization work for your ply strategy. I'm going to wrap up by letting you know how you can access our software and other ways that you can get help from us. So you can apply for a student competition bundle here, and that will give you commercial versions for all of the software listed here. Please allow about a week to hear back from us on that application. Or with a student edition, you can get those a little bit more quickly and you don't need to do as much paperwork with your team. That gives you access to this set of software, and these models are all limited in model size. But you don't need to be a member of the student team to try our software that way, as long as you're a student or a professor. I have these links in the chat, or if you're watching on YouTube, these links are in the description. I also have some links for YouTube videos and documentation that are relevant to the projects that I showed today. We have 2 webinars coming up. Again, composites next week and generative design with MSC Nastran Sol 200 Neo 2 weeks from today. You can follow along with the webinar series at our Sim Companion page, and that's where you'll be able to download, again, model files, scripts, things like that, the aluminum property file that I showed you in this demo. The webinar recordings are at our YouTube channel, and you can follow us on LinkedIn for updates. My job is to be a consultant for students and professors, and I do a lot of work with finite element. I'm interested in pioneering ways that we can use our finite element software for formula. And so if you want help with coming up with ways to do stress analysis on parts for your formula vehicle, doing nonlinear analysis on your exact composite panel issue, if you have issues setting up a composite panel model, if you wanted to come up with a streamlined way to bring in your hard points from atoms and kind of build a truss around that to have a space frame and get that geometry built in an efficient way in Apex, that's the kind of thing that I could help with, and I would appreciate it if people would reach out to me, and I am here to help you with that kind of thing. With that, I am ready for your questions.
So Alex, what are some common missteps or issues encountered when working with MSC Apex? And how do you overcome those hurdles?
That's a great question. So one of them is with loads. When we're working with solid elements, we normally want to use pressure total load in Apex to get load applied across a surface, or we could use RBEs, but we normally don't want to use the force tool without using those discrete ties. I actually have a video that's all about that, and the link for that is in the description. Another common issue that people have is with material assignment, and I was careful to point out the 3 steps for assigning material properties. Finally, when you create loads and constraints, those are not always automatically brought into your simulation scenario. And where people really run into problems is if they create a simulation, maybe they have it under constrained, and so it's unstable, they aren't able to get linear results. and then they go back, create a new constraint, but they forget to add it to the scenario. So you want to make sure that you don't just create the loads and constraints, but you need to add them into the scenario in the study tab every time to be able to make sure that they're incorporated into your model.
Thank you. Another question I see. How fine of a mesh is needed? Like, is there a rule of thumb that you follow, or do you do a mesh sensitivity study? How would a user know?
That is something that depends a lot on the context and a lot on your simulation goals. If you wanted to do a dynamic analysis or a loads model in a large structure, then you could get by with a pretty coarse mesh. But if what you really wanted to know was stress, then you need to have a refined mesh, at least in the vicinity of stress razors or other critical points for failure. Normally, if we're looking at a part that's in bending, we want to make sure that we have at least 2 quadratic elements, and ideally at least 3 elements across the thickness. But with every element that you use, if you make the mesh a little bit finer, say by cutting it in half, that can mean that you're using 8 times as many elements, and that computational cost can add up. Apex also has tools. I didn't go over that today, but tools that let you make the mesh be much finer in the regions of interest for you. So the answer is, it depends, it's context dependent, but in general, you want at least 3 elements across the thickness of the part if you can manage it, and you might need many more nodes near sites of stress concentration. That can also depend on the industry that you're in. I know of some companies where they require engineers to actually have 60 element edges around the edge of a hole if they need to extract load information, if they need to extract stress information from that hole to be able to get a result that they feel very confident with. And when in doubt, you can do a mesh sensitivity study, right? You can double the fineness of the mesh and, double it again until you get a converged result. But doing a global refinement study like that can be prohibitively expensive for anything that's more complex than just a teaching example.
Okay, thank you. And I think that is all the questions I see.
All right, well, thanks for moderating, Alex R. This was a lot of fun, and thank you to the people who attended. Okay, well, with that, I look forward to next week's webinar on Digimat, being able to see how much farther we can get with composites using Hexagon technology. And in 2 weeks, the webinar on generative design. I think that that's a really fascinating topic. Okay, thanks everyone. Have a great day. Bye.